What's that? Can't imagine.
My joints hurt now. I can't imagine when I'm like 40, 50 years old.
Yeah, 40 or 50.
Oh, God.
Basically like a dead person.
Oh, God. What have I done? I'm just scared I can't walk like I'm 50.
Okay, let's get started, please. So, there's one thing left in.
I'm a horrible person.
Okay, so there's one thing left in 5.4, and that is the notion of norms. So, norms, right, of magnitude. Okay, so right, we are doing inner product spaces. Once you have an inner product space, then it makes sense to talk about norms. But even if you don't have an inner product space, you can still talk about norms. Okay, so you can talk about norms. A norm is just something that satisfies certain rules. Okay, so here's the definition of a norm. Be a vector space. Be a vector space if there exists a function going from B to R such that this function is always positive or non-negative with equality occurring if and only if v equals 0. So that is, we have the norm would be 0 if and only if if and only if the vector is 0. 2, whenever you scale something and take the norm of it, then that's the same thing as the absolute value of the scalar times the norm of the vector. And so for all scalars at alpha. And 3, you'd like your norm to satisfy a triangle inequality. Right, for all B and W and V. If all these things happen, then we call this function a norm. And say V is a normed linear space. A normed linear space or a normed vector space. Linear space and vector space are the same thing. Okay, so here are some examples of norms, important norms. Okay, the first is so these guys are all on Rn. V equals Rn. We call this thing the sum of the absolute values of the components, the little L1 norm. Okay, so you have your vector, your vector is v1 through vn, right? And you take the absolute values of all those guys and you sum them all together. Okay? And that thing is you call that thing the little L1 norm. And you'll notice that it actually does satisfy all of these things. That it's always going to be positive, it's always going to be non-negative, it's 0 if and only if the vector is 0. Right? It satisfies the scaling condition and it satisfies the triangle inequality too. Mainly because precisely because the absolute value satisfies the triangle inequality. So that's the little L1 norm. Another one is this one. You take, instead of the sum of the absolute values, you take the peak powers of the absolute value. This one here. Okay. And then you take the peak root of that in the end. And that's called the little LP norm. And then the last one, little L infinity, you take the maximum of the absolute values of the maximum of the absolute values of those things. Okay. I'm sorry, that's not the last one. Probably the most important one for us is this one. Whenever you have an inner product space, then the inner product of a vector against itself to the 1/2 power is a norm. And then, sort of the usual remark, once you have a norm, given a normed vector space, V, one defines the distance between two vectors as just the norm of the difference. Usually you can define it, given a norm, you can define a distance. Just for practice, let's take a look at this last thing and make sure that it is a norm. Okay. So does it satisfy the first one? Do you always get something greater than or equal to 0? And you only get 0 if and only if the vector is 0. Right. So remember, suppose you have a vector and it's got an inner vector space and it has an inner product on it. Right. Now we're going to create a norm. Say the norm is going to be the inner product of a vector against itself to the 1/2 power. Right? Is that going to be is that really a norm? Right? Well, it has to satisfy all these things, right? So does it satisfy the first one? You know it does. Why does it? Why does it satisfy the first one? Can anyone tell me why? It's not hard. You just have to say, yeah.
Because you take the absolute values of. Never mind.
So this is actually, don't worry. Just remember, this is actually, I think probably you've forgotten what the definition of an inner product is. Right. So just remember, right? We had this. There was a bunch of things that we said about the inner product. Right. So the inner product, has these three properties. This is going to be greater than or equal to 0. It's going to be equal to 0 if and only if v equals 0, etc., etc. So this is actually built into the definition of inner product. Right? This first property of norms is actually built into the first part of the definition of inner product. So an inner product was something that, you remember, the first property of inner product was that the inner product of a vector against itself is always going to be greater than or equal to 0, right? So when we define our norm using this inner product, well, then of course the norm is going to be greater than or equal to 0. Yeah.
So when you're taking the square root effect, why do you get the negative root?
No, that the square root is always going to denote the positive square root. Okay. And then the second one also follows easily. Let's look at the third one. Okay, look at the third one. Why should it be true that the norm of a sum? Why should it be true that the norm? Why is it true? Is it true that the norm of a sum is going to be smaller than the sum of the norms? This thing here is going to be b plus w, b plus w to the 1/2. Right, this thing here is bv to the 1/2. This thing here is ww to the 1/2. Yeah.
Can't you use the third property of inner product spaces?
Okay.
And so you can like break your pad.
Okay, so we know, let's ignore the 1/2 for a second, right? This is going to be VB, right, plus BW plus WB, right, plus WW, right, everything to the 1/2. Okay.
Those cancel, like, right?
Well,
They equal 0 by orthogonality?
they're not orthogonal.
Okay.
Like, we don't know that they're orthogonal. I actually haven't thought about this, so I'm actually a little bit. Let's think. Why? We should be able to figure it out. Why is this true? We're trying to show that this is less than that. Right? That's going to be the same thing as showing that, the typical game that one plays is these guys are all positive, so we know that it's the same thing as showing that this thing squared is less than this thing squared, right? Right. This is what we want to show, right? Well, this thing squared on the left, this thing on the left is b plus w, b plus w. This thing on the right, is going to be, right, b squared plus 2bw plus w squared. Right. This thing here, of course, is bv. This thing here is bw, right? Not ww. Right. And then we have 2bw. Okay. Yeah. Okay. right? So you see what's going to happen, right? Right. On the left-hand side, using distributing, right, you get VV plus 2VW plus WW. These guys cancel, right? And then the question is 2V.W smaller than or equal to the norm of V times the norm of W? And is that true? Certainly, by Cauchy-Schwarz. So yeah, so the third property is does fall. Okay. Cauchy-Schwarz says exactly this. It says this, in fact, that the absolute value of the dot product of the inner product is less than or equal to the product of the magnitudes. Okay. Any questions on this? Norms are useful in reality. For example, if you're creating an approximation of a picture, suppose you take a picture, right? You take a picture, and then you want to compress it, right? Well, when you compress it, you want to throw out some stuff, right? You want to throw out some stuff so that you can. You actually want to throw out a lot of information and keep only a certain amount of information, right? But you want what you have left to be close to the original picture, right? You want it to be close to the original picture. What does that mean, close? Right? What does it mean to be close to the original picture? How do you measure the distance between a picture and a picture? Right? Close should mean that it's close to the human eye, right? So that when a person looks at it, it looks pretty much like the same picture, even though you've lost 90% of the information in it. Okay. So what does close mean? Right? What does close mean? What's the mathematical definition of close? Right? It turns out that close, it depends on who you are. For some people, L1 is close. For some people, L2 is close. So that is when they compress a picture, there are a couple ways of doing it, and the ways that do it, some of the ways I think some of the old ways of doing it depended on L1 distance, and in fact it turns out that for different people, closeness, different compressions work better. I forget which one is more common. I think there are only a few people who see closeness with regard to one of these norms, and then the other one is far more common. A friend of mine had a lecture where he like a popular mathematics lecture where he'd talk about this, and he'd show people these approximations, and then from showing them some basic pictures, he could tell what kind of distance would be more appropriate for them. Okay. Okay. So let's go on to section 5.5. 5.5. We're not going to do 5.6. 5.6 is on something called the Gram-Schmidt orthonormalization, which is important, but I don't want to do it.
Valid.
It's important, but it's not. I'll tell you what it is. I will tell you what it is, and I'll let you look at it if you want. You can look at it if you want. Okay, so orthonormal sets the idea is that you want something like in an abstract vector space, something analogous to the standard basis E1 through En. Right? Because this basis is not just any basis. You know, it's well, for one, everything is orthogonal to each other. Right? Further, everything is of unit length. Right? So you would like to have something like this in the in an abstract vector space. So V in your product space, V1 through Vn, non-zero vectors. If Vi is perpendicular to Vj for all I not equal to j, then we call V1 through Vn an orthogonal set of vectors. Right. So for example, if V is the continuous functions on negative pi pi, and we define an inner product on this by integral of f against g over the integral and dividing by pi, then in fact, if we look at, say, 1 cosine x, cosine 2x, cosine nx, this set of functions is orthogonal. So this set of functions is actually an orthogonal set under this inner product. It's a calculus exercise if you want to do it. And you have to see that if you multiply any of these guys together and integrate them from negative pi to pi, you get 0. In fact, even if we throw in sine functions, that's still, we throw in all these guys together, they're in fact all orthogonal to each other. So properties of orthogonal sets. So here's a property of orthogonal sets. So V and inner product space. If your set is orthogonal, then in fact your vectors are linearly independent. Your vectors are going to be linearly independent. Take a couple minutes and see if you can figure out why that happens. Remember what linearly independent means? some combination of it is the zero vector, then all the coefficients must be 0. And so what we're saying is that if the guys are all perpendicular to each other, then it's going to force, if they're all perpendicular to each other and you take linear combinations of them that yield the zero vector, then it must have been the zero combination. Can you turn to somebody next to you and help them for a little bit?
I suspect it was the
So, suppose that you have some combination that yields a zero vector. Suppose you have some combination that yields a zero vector. Right? You know these guys are orthogonal to each other. Right? You're hoping to see that right? You're hoping to see that you want to show that Ci equals 0 for all. Okay. Well, you have only one thing, right? You have only one fact to use, which is that V1 through Vn are orthogonal to each other. So how do we use it? Right. So this is an orthogonal set. Right, so what do we know? These are all non-zero guys, and they're all perpendicular to each other. Yeah, Mia.
If you do the dot product.
Yeah. Okay, so what are we going to dot? What are we going to dot against?
The orthogonal set.
We're going to dot this thing, or what are you going to dot?
That against the orthogonal set.
Okay, so let's dot. Consider then the vector, this thing, dotted against some Vj. Okay, where J is one of the guys from fix a j. Right? J is one of these things from 1 to n, and we take the dot, we take this thing. What happens?
Equals 0.
We're going to get 0 for everything except for when I equals j. Right? When I equals j, right? So what this picks off is Cj. Vj dotted against any other one is going to be 0. But when I equals j, then we get Cj, Vj, Vj, Vj. Okay. So does that tell us that Cj is equal to 0? Sure, right? Because
Because you can't do that with itself unless V is equal. Like they can't equal 0.
are you saying that this equals 0?
Well, that can't equal 0.
This is not
unless
equal to
V
0.
is equal.
This is not equal to 0, right? So that tells you that this must be equal to 0 because this thing on the left side is 0. Right? You're taking the 0 vector dotted against something. The 0 vector dotted against Vj is 0, right? So you get 0 equals Cj times this non-zero number, right? Right. What we get is that Cj, right? 0 is Cj times this non-zero number, and so Cj must be 0. Right? And so Cj must be 0 for every j. Pick any j between 1 and n, we see that Cj is 0. You got it? Everyone get it? Okay. Right. So we see that each one of the coefficients must be 0. Okay. So right. So whenever you have an orthogonal set, then they're linearly independent, and right. So in particular, right, any orthogonal set is then a basis for its span. Okay. A remark. Notice if the VI's all have norm 1, for all I in the above, then this inner product would give us Ci, right? Because we would get, would give us Cj, right? Because we would get Cj, Vj, Vj. But Vj dotted against Vj is 1, right? So we could pick off, i.e., we can pick off the jth coefficient by taking the inner product against Vj. Right. So we can tell how much of Vj is in there by taking this inner product. Okay, a couple of sort of not exciting statements. First is the definition of orthonormal set. So V1 through Vn, an orthogonal set. If all the norms are 1, then we call the set orthonormal. if everything has norm 1, you call it orthonormal. And of course, if you have an orthogonal set, you can make an orthonormal set out of it just by dividing by the norms. Right? So if you have V1 through Vn orthogonal, then just normalize everybody and you get an orthonormal set. Right, so for example, if we look at this set here, this was an orthogonal set. This was an orthogonal set, and if you calculate it, the norm of 1 is square root of 2. And the norm of all these other guys turns out to be 1. So all these guys turn out to be 1. And so to make this an orthonormal set, we just need to normalize this first guy. And now we have an orthonormal set. And then there's the most boring definition of all, a basis that is orthonormal. Normal is called an orthonormal basis. You guys wrote it down. Okay. That's actually true. I'm not joking. That's okay. Useful properties of orthonormal bases. Orthonormal bases. First is the one that you already noticed, that if U1 through UN is an orthonormal basis for V, and V equals summation Ci Ui, then Ci can be picked off by taking V against Ui. Okay. So for example, if you have a function, and that function is some combination of cosines. Suppose you have your function, and your function is some combination of cosines. Then we can determine the coefficients. Okay. Just take your function and inner product it against the elementary cosine function. So you take your function Ci, then it's going to be just the dot product, the inner product of f against the ith cosine, which you can use ck. And you can figure out how much of that cosine wave is in there by taking the inner product of it against that wave. and that's actually, the idea. That's actually how one digitizes music. Like you take your function sounds are combinations of waves, and then you figure out what waves are in there by dot product, taking the dot product against those waves, and that will tell you the coefficients that you need to have to reconstruct your original sound. I'll say more about that in a second. Okay. So a corollary of the theorem. If you have U1 through UN, an orthonormal basis of the inner product space V. If U is some combination AI UI, and V is some combination BI UI, then UV, the inner product of U against V, is going to be, well, what do you think it's going to be? Maybe I should tell you. It's going to be, in fact, AI BI from I equals 1 to n. So what this tells you is that, right, that the you have this inner product space, right? You have this inner product space, and the dot product, the scalar product, right? You have an inner product space. Just here it is. Right? The inner product of these two vectors is going to be the dot product of the coefficients of those vectors. Right? Each of those vectors, right? Each of those vectors is in your space. It's a linear combination of the UI, right? And it turns out that the inner product of this is going to be the dot product of the vectors of the coefficients. Okay, so basically what you have here is some sort of analogy. Right? Like, here's your inner product space, right? V and inner product space, and then here is little L2. Okay, little L2, just the set of or maybe let me say it like this. Okay. So here you have your vector, right? Here you have V, and here's the vector U, and right, it corresponds to A1, A2, AN. Right, and then you have V here, corresponding to B1 through Bn. Right. The inner product here, what this corollary says is that the inner product here actually equals, the Euclidean inner product down here. Okay, so here down here you have maybe you think of it as Rn. You've got Rn down here, right? And so the inner product space somehow parallels. If you can put an orthonormal basis on it, then the inner product space very directly parallels Rn. Okay, so let's prove this statement. Right? Why does it happen? Right? So let's think. U inner product U inner product V, well, that's going to be U against V. Right, which I'm gonna, I can pull out the sum here. From 1 to n. I can pull out the scalar. So I use linearity. I pull the scalar out. I pull the sum and the scalar out. Right. But this thing here, ui against v, what's that? It's bi, right? It's bi. Right. So that's it. Right. So the dot product of these two vectors in the inner product space is just going to be the dot product of the coefficients with respect to an orthonormal basis. As a corollary of the corollary, one has something called Parseval's formula. That if you, if V equals summation Ci Ui, then the norm of V square is going to be the sum of Ci squared. But that's just an immediate consequence of the previous. Right? You know that uv is going to be summation ai bi, and so if you take vv, then that's just going to be the sum of the coefficient squared. Okay, that's it for today.